and welcome to Chapter 10. Chapter 10, we're going to cover the concept of transaction management. So we've already covered transactions kind of in a generic sense, both with your stored procedures and your triggers. Now we're going to talk about how to manage those transactions to make sure that we keep our data integrity and we have what we call concurrency control. Let's get started. So the first question to ask is, what is a transaction? So when we think about a transaction, we use the phrase a logical unit of work. So an example of that is the collection of steps that we need to take to complete a single task. This can all be combined into a single thing. When we talk about things in coding, sometimes we talk about functions or we talk about modules, things that can be combined into a single unit. In this case, we're making a logical unit of work, things that all these things have to occur together. It can include one or more actions. It could be just a single action or it could be multiple, but each action is going to rely on the previous actions. They're all going to be kind of combined together. If any part of this workflow fails, it's really important that the whole transaction should fail, because if we're looking at a logical unit of work, it's really important to make sure that that logical unit of work gets completed to its end. If we only did part of it, all of our data would be a little bit off. So in databases, a transaction can contain multiple SQL statements. But if any one of those SQL statements fails for any reason, the entire transaction should be what we call rollback. An example of this would be a customer comes in and purchases something. So we're going to do 4 items every time this happens. We are going to write out the customer's invoice, including those line items for each product. We're going to reduce the quantity on hand because we're taking it out of inventory. We are going to update the account transactions so that we can point out that the customer actually paid for it. And we're going to update their customer balance. So their balance is how much do they have on credit. So if they bought on credit, we need to update that balance to either add that amount to the balance, or if they did a transaction, we don't need to update that. But these are all kind of combined together in fulfilling a customer's request. You can see how if we did the first 2, but we forgot to do the 3rd and the 4th, things are going to be a little weird. We didn't get the account transaction done, so we aren't sure that they paid for it, and their customer balance wasn't updated because we had a problem somewhere there. If we tried to reduce the quantity on hand to say that we took these out of inventory and we somehow ended up with a negative number, we took out more than existed, well, now we've got another problem. That one failed, which means our quantity on hand didn't get updated. So when you look at this entire transaction or logical unit of work, you want to think of all of these as either they all occurred or none of them occurred. Transactions are collected to create what we call a consistent database state, where the data integrity is always preserved. If we're looking at our data, remember, it's all about data integrity. We have to make sure that the data is accurate. If we don't roll back the transaction with a failure or commit it when we get all 4 of them done, then our database state might be a little bit off. Our quantity on hand might be off. Our amount of dollars in the till might be off. Our customer's balance might be off. Transaction might not have been added. So it's important to keep all of these straight when we are doing our transaction. Now we're going to start working with how do we build those and what is going to happen with that transaction. So it's important when we do a transaction that we evaluate the results and make sure that everything occurred correctly. A transaction doesn't technically have to change the database. It can, but you can have statements in there that are select statements, just checking values. If the values were all good, then everything's fine. Don't change anything at all. So you can have a transaction that doesn't actually change the database, but any SQL statement that actually accesses the database can be included in a transaction. The assumption in this example that I've given you is that we already know the customer, the invoice, the transaction numbers, the product code, the quantity, and then the prices, and we've hard-coded those in. In reality, this transaction would probably take those either as parameters, or they would calculate them as the new inserted if this was in a trigger, or if it was a stored procedure, they would take them in as inputs. So in this case, we're just hard coding in the numbers. But you can see I've taken the 5 things or the 4 things that we did on the previous page, and I've created SQL statements for each of them. we need to insert the invoice. So inserting the invoice includes two invoice insert statements. First, we need to insert into the invoice, and we need to insert into the line item, because remember, each line item, in this case, the user has purchased a single item. That item cost $256.99. There was $20.56 of tax for a total of $277.55. He put it on credit, and we charged $277.55 into his credit account. He has a user number, a customer number, and an invoice number. We use those information to update the quantity on hand. This would be something similar to the trigger that was in your homework. Updating the quantity on hand to reduce the quantity on hand by 1, because he only bought 1 of the item. And that was the product code. So again, we would have gotten that somehow in a select statement. We're going to update their credit balance. So we're going to go back to the customer table, and we're going to update the customer balance by adding the $277.55 to their current balance. And then we are going to insert a charge into the new account transaction table. The last time we dealt with Sale Company, we didn't have a transaction table. We've added one since then. So we're going to insert in there saying that we have inserted a transaction with this customer ID and this dollar amount, and it was a charge. The important thing with the transaction, after the transaction is over, you want to make sure that you go back to your tables and check them. Verify all of the entries that should have been added or updated, deleted, whatever they needed to be. So the first couple of times you write your transaction, you want to write your transaction, run your transaction, and then make sure you do some select queries to verify your results. The DBMS cannot guarantee that you coded it correctly. As I always say with coding, you can guarantee that it ran, but you can't guarantee that the algorithm was right, because the program does exactly what you told it to do. All right, so there's a lot of different properties that go with transactions, and we call them the asset test because we call each of the 4 properties that we want to talk about ACID, so it's the asset test. The first one is called atomicity, or atomicity, depending on how you pronounce it. This simply says that the transaction is either successful or not successful. Did all of the operations occur in the transaction, and did they all occur successfully? Otherwise, abort all of it. Don't run any of it, because you don't want to do just some actions from the transaction and not others. So it's really important that in our transaction, we have this concept of atomicity, where everything is either true or false, successful or not successful. There's no partial in the middle there. The second is consistency. The database state must be consistent, making sure that all of your constraints are always met by the time you get to the end of the transaction. Obviously, if we're inserting records into a table and we need to make sure that the foreign key exists and the primary key exists and so on and so forth, we can insert a record that should have a foreign key, but the foreign key hasn't been built yet, so we have to build that and we have to add this. So there will be moments in the middle of your transaction where you will not have consistency. You will not have all of your constraints being met. But by the time you get to the end of your transaction and you commit it and you're done, all of your constraints should be true at this point. So it's okay in the middle of your transaction while you're adding things to have breaking of those requirements or constraints, as long as by the end they're all back to consistent. So that consistency simply means that the state at the beginning of the transaction, in other words, all of your constraints were true, must be the same state that it was at the end. All your constraints have to be true as well. We have a concept called isolation. And the isolation simply means that each table and field for the transaction cannot be changed by something else while the transaction is executing. We're going to go over this a little bit further when we get into data logs. The concept is that no data items can be used by a second transaction until the first one is complete. You can imagine you have 2 transactions and they're both editing the same table. How does that work? Can you do that? Is that allowed to be able to have 2 different tables editing the same piece of information? Well, no, that wouldn't be consistent. Your data integrity would be off. So isolation simply means when we look at our data, we look at our transactions, it's really important for that data to only be touched or modified by a single transaction at a time. When that transaction's over, we can move on to the second transaction, but in the meantime, All the data can only be affected by one transaction at a time. And the last one in the ACID test is durability. That simply means that once the transaction has been committed, it cannot be undone. Power failure, system failures are not going to affect it. It's kind of like hitting the save button on a Word document. You type in the document, and it's kind of got that autosave that kind of works, but it doesn't work like 100% all of the time. But as soon as you hit that save button, now you know it's saved. You can shut your computer off, turn it back on, and you know the data will still be there. So that's going to be your durability part of this entire thing. You want to make sure that power failures and system failures are not going to be a problem. There's an extra added attribute that is not part of the ACID test, but is still part of the transaction properties, which is its serializability. Is it ability to be serialized? Serialized meaning, can you have two things occurring at the same time, or do they have to be sequential? Can you have concurrent transactions and still get the same result? Well, if I'm editing table A with one transaction and I'm editing table B with a second transaction, sometimes it might be okay, unless I'm using values from table A in my update, things like this. So if you had 3 different transactions, what order are they processed in? Do they have to be processed separately, or can they be done in sequence? If the transaction can be done in sequence and concurrent with the same results, so if you did them 1, 2, 3 in order, all of 1, all of 2, all of 3, or if you did 1, 2, 3 all at the same time, would you get the same results? If you would, then those transactions are serializable. So it's important to know the difference. If it is serializable, that means that it cannot be affected by the other transactions in the group. If it is not serializable, that means we cannot do them concurrently. We have to do them in sequence so that one occurs before the other. And again, we'll talk about this along with data locks a little bit later. So I've given you an example here of the transaction management that we do in SQL. Remember that this is in SQL Server, and if you were doing this in Oracle and PL SQL, it would be a little bit different syntax. This is the syntax straight out of the SQL documentation. When we do a transaction, there are options of what I call try-catch blocks. If you've done coding, you know about try-catch blocks. If there is an error, if there is something that occurs that makes it so that things don't work right, you have to be able to roll back your transaction. So what we do is we start the transaction by using begin. So we say begin transaction. You can give it a name, by the way. You can say begin transaction T1 so that you can edit specifically that transaction or roll back that transaction rather than just a generic transaction. And then we can begin our try for our try catch block. Inside of that, we can run a piece of code. In this case, I'm deleting, but that's going to cause a constraint violation, which is going to cause my SQL to crash. Same way it does in code. When you do a try catch block, if you get an error, it jumps down to the catch. So in this case, if I'm deleting from the product where the product ID is 980, well, that's in a constraint. It's a foreign key somewhere else. You can't delete it. So it's not allowed to be deleted. So the SQL is going to yell at you and say, no, that's not okay. And then we're going to run into our catch. In our catch, we like to do a comparator to say, if there are any transactions that are being held, waiting to be committed, then we want to roll back. So we can do the keyword ampersand ampersand tran count, which is transaction count, how many transactions have, or how many counts of statements have been run by this point. Do we have to roll back anything? If it's 0, that means nothing has been done. There's nothing to roll back. We'll just stop. We're good. But if I have done 5 other statements up to this point, then that tran count is going to come back as 5 and say, hey, you've done 3 updates and 2 deletes. Are you, we have to roll that back. So in that case, because we had an error and we can't continue on, we need to roll back our entire transaction. When we fall out of our try catch block, then I can check with that tran count again to make sure that I need to commit my transaction. If you've already rolled back the transaction and you call commit after it, it's fine. It's been rolled back. There's nothing to commit at this point. It may give you an error of saying there's nothing to commit, which is why we like to do this if in there just to make sure that there was something to commit. But this is the SQL syntax for beginning a transaction. It will either end with a commit or a rollback. You can begin and end your try and catch blocks just the way you would in code, and then use the comparator of the trans count to determine if you need to roll it back and if you need to commit it. By the way, if you forget to commit, which I really recommend not doing, but if you forget to commit, when you get to the end of the file, the end of the SQL file, and everything has been executed, it will automatically commit. So it commits at the end anyway, the same way if I ran 5 SQL statements without saying begin and end commit, it'll commit at the end of that. But when it comes to doing transactions, the point of commit is to keep the entire transaction as a unit, and you want to keep that together. So you always want to start with the begin and end with either a rollback or a commit. Remember also, if you do end up working with Oracle, the PL SQL syntax is a lot different than the T-SQL or transaction SQL. So the next part we're going to talk about is our transaction logs. Every time that a transaction is done in the database that is going to modify or edit or change anything, all of those transactions are stored in a log. These logs, we're going to talk about a little later with data recovery, are useful if you lose your data, if you need to recover your data. And we've kind of touched on transaction logs before, but this one gets you a little bit more detail about it. The transaction log is going to store each SQL statement that is committed, every transaction that goes through. It will store which objects are affected, what type of operation, an update, a delete, an insert, the before and after values. So what was the value in the record set before, and what was the value after? If it's an insert, there is no before value. If it's a delete, there's no after value. But the before and the after will go with updates. It will also have a pointer to the next and the previous log entry, because the logs exist as a list, as a linked list that allows you to keep track of what were the logs that were before this and what were the logs that fell after this, which allows us to keep them in sequence. It will also keep date timestamps and user stamps of who did what and what time did they get done. Transaction logs are stored in such a way that the database can use them the most efficiently, which means, yes, you can search them, and I have the SQL statement here to go look at it, but they're not going to tell you much because they don't look like normal words. It's not in text. This is some that's in binary, some that's in hexadecimal, some that's in machine language, and it means something to the DBMS, but it's not going to really mean a lot to you. So in this case, the 2 parameters that go with the DB log are telling you where do you want to start from and where do you want to end from on what page number. You can put null and null and it'll return all of them, which is fine. And you can go ahead and look at it and you can search through it and stare at it, and it probably won't help you very much, but it is there. Transaction logs, again, we're going to talk a little later on database recovery, but they will store every transaction that is done in your DBMS. All right, so concurrency. Concurrency controls offer the ability for your data in your database to stay up to date and current. Okay, so concurrency is not with money. It's not currency like money. It's up to date. It's current. So there are 4 different things that we need to keep track of when we're talking about concurrency. The first 3 of them are occurrences or situations where data is not current. The first is what we call a lost update. This occurs if 2 different transactions are trying to update the same data, and one transaction's data gets overwritten immediately by the second transaction, and you lost an update. So I'm going to set John Doe's address to 123 Main Street in transaction 1. And then in transaction 2, I'm going to set John Doe's address to 234 Main Street. Well, that first one just got lost. The update got lost. And we have to make sure we understand when there are lost updates, how to handle it and how to be prepared for it when we're making our transactions, to make sure that if we're selecting data or if we're entering data in by parameters, how that data is being retrieved, and how do you handle lost updates. What generally happens to cause a lost update is you have 2 users that are both using the system at the same time and they're updating the same fields, and one just happens right before the other because they're not talking to each other. So that occurs. The second is what we call uncommitted data. So if you have two transactions, both using the same set of data, and transaction 2 does a retrieval, a select off of the data after transaction 1 has started. So transaction 1 has started and it's updated some data and it's going along just fine, and transaction 1's hanging out over there. Transaction 2 goes and gets a select statement to get some data, and it gets the new updated values that T1 did. Cool. Transaction 2 moves on just fine. And then transaction 1 is rolled back. Once it's rolled back, because the data was uncommitted, it goes back to its previous value, but transaction 2 doesn't know that. So transaction 2 moves on as though the data that was in transaction 1 is still accurate, even though it's not. And you end up dealing with what we call uncommitted data. The data did not get committed. It actually got rolled back. It's not accurate data, but transaction 2 doesn't know that, and it needs to keep moving forward. How do we handle that? So again, these are just situations that we're going to talk about how we handle them in just a second. I want to make sure you understand the situation. And the third is inconsistent retrieval. So if T1, transaction 1, is calculating aggregate data that is being updated by other transactions, I want to get the quantity on hand, and I've got that, and I'm doing a calculation to figure out average prices, but transaction 2 just took some a new invoice and pulled down that quantity on hand, which means all my aggregates are different now because I got an inconsistent retrieval. So if I get another query that says, now give me the total of all of the sales, well, now I have the new sale that transaction 2 just submitted, but I still have the wrong quantity on hand because I got that beforehand. So you want to make sure that when you're retrieving data, if you have concurrent transactions, that you're not going to run into this inconsistent retrieval. What happens is we create what's called a scheduler or a serializer, which is a process that's going to determine the order of the transactions. So it's going to make sure that it knows which transactions touch which tables, which ones read, which ones write, which tables need to be locked down and which ones don't, how that needs to handle, to make sure that our data is serializable or scheduled in such a way that none of the data will fall into any of these three options. It'll create a schedule of the transactions to make sure that the transactions happen in an order that is the most efficient, uses the CPU well, but make sure that we do not have any of these concurrency issues. So the way we solve this is by things called locks. So we have a couple of locking methods that we're going to talk about. Locks are in place to guarantee the exclusive use of the data during the transaction. If we make the assumption that there will be conflicts, we call it pessimistic locking. We're going to plan on there being locks, and I'm going to plan on there being conflicts, and I'm going to design my database around that. So I'm going to make sure that I lock my data out when I'm doing a transaction so that I can have no conflicts and nothing will cause problems with my data integrity. There is a part of the DBMS that is going to control that. That's the lock manager, which is going to manage all of your locks. And then there are different granularities, which is the level of lock use. I can choose to lock my entire database at the database level. I'm running this transaction. I'm touching literally every table. I don't want anything reading or writing anything until I'm done. I can do that. I can do a database level lock. This is really rare. You don't really want to do this unless you absolutely have to. You'll do a database lock if you're if you're copying data across or if you're editing tables and you want to make sure nothing changes while that's going on and you don't want anything to access anything. A database lock means nothing can occur until that lock is cleared. So until that transaction has finished. The second is what we call a table level lock. I can lock the entire table. Nobody can read or write from this table until I'm done. Read or write, really important. You can have page level. So if you think about the tables might have a lot of data in them, and each page may be 4K or it may be 8K, which might only hold, say, 20 or 30 rows of a table. Well, if a table has 5,000 rows, there's a lot of different pages, and you can choose to say, I just want to do a page lock on this data because I want kind of the data that's at this place, or maybe a couple rows ahead or a couple rows behind, but I don't need I don't need the whole table locked. I just need some of the table locked. So we can do a page level lock that just locks a page. This is actually really common to use this one because it gives you kind of I'm locking the table to make sure none of the data changes, but I'm not actually not changing any data. I'm just not changing the data that I think I'm working with. Another common one is a row level. If I am working with a single record, this customer, all I need to do is lock this customer. At the row level, I just have a single record locked. That means no one can read or write from this record, but they can read and write from all of the other records in the table. This is a really common one when you're doing insert queries to verify data or something like that. I want to do an insert query. I want to lock the record. I want to be able to modify a couple of fields in there that run some verification, but I don't want to lock down the whole table. And the last one of the locking methods is a field level. Only a single field in a given row is locked during the transaction, which means I can lock down a calculated field and leave the rest of the fields to be updated if they want to be. And that's okay, but sometimes that's almost making it too low of a locking method, so we sometimes don't like to use that one. A little bit more about locks, and there's a lot of information about locks. There are different types of locks. So there is a binary or a shared exclusive lock. So binary meaning two. It's either locked or it's unlocked. Yes or no, true or false, but there is nothing in the middle between that. So a binary lock is just locked or not locked. But we also offer the option of what we call a shared or exclusive lock, which is actually a tertiary operator. We have three options. It can be unlocked, it can be shared, and it can be exclusive. So shared offers a read-only aspect to the table that is being, or to the object that's being locked, so that you can still do SQL queries against it. You can still read, you just can't write. So it's a read-only type of lock. It locks it from being able to write anything to it, but it does let you do reading. And then when you do a shared, you can offer an exclusive lock to a specific transaction. This transaction has an exclusivity of it can write to the transaction, but it's the only one that can own it. You can only have one transaction be exclusive at a time for a given object. So if I want to make this table an exclusive lock for me because I'm editing the table, but I can make it so that it can be read by other people without affecting them. So this is not the binary locked or unlocked. This is kind of a halfway locked. It's locked, but it's still readable, but you just can't write to it. Now, something that happens a lot if you have your locking badly is what we call a deadlock. Deadlock is where two or more transactions are trying to edit information and they both end up waiting on the other one. Okay, when we lock, we talk about a two-phase locking or 2PL. The two-phase locking has two different phases. It is the growing phase and the shrinking phase. So in the growing phase, the transaction is going to go through and figure out exactly which locks it needs. It's going to require all of its locks without unlocking any data. So it hasn't actually done anything yet, but it gets all of its locks in place. And then once it figures out all of its locks and they're all locked, then it locks it. So it's locked down. Then it goes and it runs all of its code while everything's locked. And then it has what's called its shrinking phase, which is where we release all of our new locks, or all of our locks. The important thing about this is that you have the locking phase and the unlocking phase. You cannot relock something in a single transaction once you've gotten to the shrinking phase. So the same way that you cannot unlock anything if you're in the growing phase. Do all of our locks, run all of our code, unlock everything. You can have no conflicting locks at all, and no unlock can precede a lock in the same transaction. Again, all your locks happen at the top, all your unlocks are at the bottom. And no data is actually manipulated until all the locks are obtained. So when we do the growing phase, and set all of our locks, then we can start modifying data. But you cannot modify data until all those locks are determined. So this is our two phase, our growing, shrinking phase of locking. A little more detail on deadlocks, just to give you an example of how deadlocks work. If you have two transactions, table 1 or transaction 1 locks table A. Transaction 2 locks table B. Cool. Table A, table B. There was no problem with that, right? But then table 1 needs table B to continue. So it's going to hang out and it's going to wait because T2 has locked table B and it's waiting for T2 to finish. T2, on the other hand, is waiting to get to table A. So it's waiting for T1 to finish so it can do table A. And they both wait forever. This is called a deadlock. It's a lock that will never go away because T1 and T2 are waiting for each other and neither of them can continue without it. Deadlocks usually have to be resolved by the DBA. What happens is your system's running fine, it's beautiful, and then it stops. Everything stops. Someone calls you and they're like, hey, there's something wrong here. I went to go look at the data and it says data is deadlocked. And I don't know what that is. And you're like, oh, crap. Okay. And then you go fix it. So you go in and you actually manually release one of the two locks and you roll back the other. So this is, deadlocks are one of those things the computer can't figure it out on your own. You have to build it. So you have to make sure when you're designing your transactions that you don't end up in a deadlock situation. Transactions have a start time and an end time. We can look at those start and end times to determine which of the two transactions that are sitting at the stoplight waiting to go, which one of those two transactions is older and which one is younger. There are two different ways to handle it, and you can tell the database with the transaction how you want to handle this. Do you want to do a wait and die, or a wound and wait? So wait die is a style that says the older transaction, the one that started first, will wait until the younger transaction releases its locks. If the transaction is younger, it will die. It will roll back and release its locks and then be rescheduled using its original timestamp. So if I have the older one is set at 12 o'clock and the younger one is set at 1 o'clock, okay, so the younger one dies, it gets rolled back, and it gets rescheduled still with that 1 o'clock timestamp. The older one, as soon as the younger one has released its locks, will be able to finish and move on. If another transaction comes in with that 2 o'clock timestamp, it's okay because the younger one is still now the older of those two, so it will go next. So being able to do the wait or die concurrency allows each one to decide who gets to go next by whether or not it's older or younger. The wound and wait also goes back to the older and younger concept, but what happens is the transaction that is requesting the lock is older. It will automatically roll back the younger transaction, wound it. So we're preempting that rollback. Instead of letting it die on its own, we're going to roll it back for you. If the transaction requesting the lock is younger, it will just wait for the other transaction to finish. So we're going to look at this and determine whether or not we get to roll back the one that's holding up our data or whether we're just going to wait. It's okay to wait because if you're the younger one, you can just hang out for a little bit and wait and see until the older one finishes. It may not be totally locked at this point. It may just be waiting, and that's okay. The older one is going to say, hey, this youngin's in there and he's annoying, so I'm just going to go ahead and preemptively roll him back, tell him to come back later, and I'm going to go run my stuff. So wait and die versus wound and wait determines what's the correct order to handle concurrency based on the timestamp, whatever the time is that transaction started. So a lot of the things we've been talking about are pessimistic methods or approaches towards locking data. We're assuming that there's going to be conflicts, and so we're prepared with all these locks and all these different ways of handling it. But sometimes you look at your data and go, nothing's going to actually conflict. There's not that many changes to my data, so I don't really need to worry about it. So this is taking an optimistic approach. We're not going to have conflicts. I'm not even concerned. When you do this, if you do the optimistic approach, you run in the possibility of having 3 phases. You run your transaction and you do your reads. So you read all of your values, you execute all your computations, and you create a private copy of the database tables in a temp table. Okay, cool. Then I'm going to run through a validation test to make sure that nothing has changed since the beginning of my transaction up to now. So I'm going to check and make sure that nothing affecting my integrity or my consistency is a problem. Check all my values, my tables, my methods, make sure nothing's changed. If it's still valid, keep going. And if it's not valid, go ahead and roll it back and then start again. So we're just going to do was this good? Nope, that wasn't good. Let's go try it again. Was this good? Nope, not good. Let's try it again. Was this good? Yes. Okay, cool. Now we can go down to the write phase, which is the third phase, where all the data is finally written to the database permanently. This is inefficient if you have a lot of conflicts, but if you don't have a lot of conflicts, most of the time your data is going to be valid and it's going to go ahead and go to the write phase without a problem, because the way your data is created or the way your data is being used by your application doesn't actually have a problem with conflicts most of the time. This is really common if you have a system that does a whole lot of reading and not a whole lot of writing. So you're doing a whole lot of select statements. Most of your application is looking at data, viewing data, reporting on data, but there's not a whole lot of adding new data. There's not a lot of updates or inserts. It's just a lot of reading. In this case, you're not going to end up with a lot of conflicts because you're not going to be changing data all that often. You're not going to be running transactions with a bunch of updates if updates don't occur that often anyway. So in these cases, it's okay to do the optimistic method or the optimistic approach of being able to read everything in, store it in temp table, go check and make sure that nothing's been changed, and then go write it all out to the database. Once we have our data, we need to understand the level of isolation. So we talked about isolation. In this case, this is the ANSI level of transaction isolation. And there's 3 different ways that data can be a problem. The first is called a dirty read, which is reading the uncommitted data. We kind of referred to this one. So data was uncommitted, but we write it anyway because data was just updated and it could have been rolled back, but it hasn't been. Right now, it's just uncommitted data. There is a non-repeatable read, which says that the same select statement, the same row, gives different results at different points in your transaction. In other words, you read it at the top of your transaction, then you read something again 3 levels down, and you get different results. That's not good. And the last is what we call a phantom read, which is reading at different times gives you different results, which is similar to the non-repeatable read. So reading at different times, depending on how things are going, can give different results, and it's just a read that kind of confuses you. There are 4 different transaction isolation levels that you can pick from. The first is being able to read anything you want. Read all of the data that's dirty, all of the non-repeatable, and all of the phantom reads. There are no locks. It's all good. You can read data from uncommitteds. You can have non-repeatables. You're all good. All different types are allowed. The default for both SQL Server and Oracle is a read committed. It'll only read committed data, so there'll be no dirty reads, but they will allow non-repeatables and phantom reads by using exclusive locks. So we'll put in exclusive locks in our code to make sure that you can write in your transaction, but you can only read. Remember that shared exclusive. And so you can do the non-repeatable and phantom reads. Sometimes those occur because we're not doing uncommitted data. We're only doing committed data, but we do have those locks in place. So we have to make sure we use those locks to make sure that our data stays safe. You can also set it up with a repeatable read, which requires that all the results are repeatable. So we cannot have our dirty reads or our non-repeatables, but we still can allow phantom reads. This is where we do our shared locks. So this is where you allow there to be locks, but they're that read-only lock so that you can read things that just haven't finished yet and they might not be the same result, that phantom read, but at least they're not just randomly different results and it's not dirty reads. And then the most exclusive, the most restrictive is not allowing dirty reads, non-repeatable, or phantom reads. You have locks that are Boolean locks, that are binary locks, either on or off. It's the most restrictive. SQL Server and Oracle will do the read committed. And I have the syntax up here for SQL Server on how to set your transaction isolation level. So you simply say set transaction isolation level and then pick one of these. So either your read uncommitted, your read committed, your repeatable read, serializable, and then SQL Server offers also a snapshot, which is take a snapshot of the database right now and use that throughout your entire transaction. So different levels of isolation for your transaction, and when you would want to do one or the other. Do you want there to be exclusive locks? Do you want it to be shared locks? Do you want it to be binary locks? How do you want to handle, or do you want to do no locks because you don't worry about the locks? So you can think about those while you're writing your transactions. All right, so sometimes in the universe, you need to recover your database. Your database did something bad and it's not in a consistent state. There's something wrong. So database recovery is simply the process of restoring from the current, which is currently an inconsistent state, to a previously consistent state. Again, we have that atomic transaction property, which is where all portions of the transaction have to work as a single unit of work. When we think about transaction recovery or database recovery, we're thinking about individual transactions. So we're not going to do individual SQL statements. We're just going to do the transactions as a whole. There are 3 different styles of failures that can occur that will cause problems with your database. The first is the hardware software failures. You actually had a failed disk. The application actually crashed and you ended up with some problems with the application. These are, the application errors is probably one of the more common ones. You wrote code in your application that you're using that broke your database. This happens, and you have to sometimes recover your database because something didn't get stored correctly and now your database is in an inconsistent state. You can have human-caused incidents. This is an unintentional user error, somebody data entered wrong, and of course the intentional. These are the hackers. We don't like them. And then of course there's always the God-made natural disasters, fire, earthquake, floods, and the power went out. Not like that ever happens in Montana. So when we want to recover our database, one of these things has occurred and we have to figure out how to get our data back. There's a couple of different things to keep track of when you're doing database recovery. We can have the concept of a write-ahead log, which is where you write to the database log before the data is actually updated. So we're going to write that log. Remember we talked about that transaction log. We're going to write our transaction log before we actually try to update the data. That means that at any given point, if we can get to that transaction log, that will give us everything up to this point. If something failed in the middle of the transaction, that's okay because we can go back because we have a log for that. We can have redundant transaction logs. This is like those people that store 12 different versions of their backup. Like I'm going to do a backup every day and I'm going to have 31 versions of my backup and I'm going to hold them all. This is storing multiple copies of your transaction logs so that if any one moment you find that your data inconsistency happened 4 days ago, I can go back to 4 days ago and get the transaction logs at that point to reset things because none of the data after that was accurate. You can have multiple copies of your transaction logs. Sometimes we use buffers so we can temporarily store our data storage and then tell it later, go ahead and finally update all the buffers. So you run 4 updates, 3 inserts, you throw them in a buffer. Then you run 3 more updates, 2 more inserts, throw those in a buffer. And finally, an hour later, you run all of your buffer. So you can have buffers that store your data and do it that way. And then there's an important part called a checkpoint. The checkpoint tells you update all of the buffers at the same time, but lock down the database while you're doing it. So this is kind of one of those things where if you have an application and you want to run a checkpoint at midnight every day because no one's using the system, you're going to lock the whole database and run everything through a checkpoint. The nice thing with this is if you do it at 2 in the morning when no one's using your system, nobody cares that you locked down the database and nothing can be accessed because no one's going to be doing anything at 2 in the morning. And you're allowed to have a checkpoint. If you have those checkpoints, you can use those for data recovery. So 2 different ways of doing database recovery. We can use our deferred write or our write through. So with a deferred write, you go and you find the last checkpoint. If a transaction was started and committed before the checkpoint, then I don't care, because the checkpoint is going to point out a single point that everything was up to date at that point. So I don't have to do anything with anything that was done before the checkpoint. I only have to look at the transaction logs from the checkpoint forward. Now, in that transaction log, you're going to find two different types of transactions. A transaction that was committed after the checkpoint, or a transaction that was rolled back. If the transaction was committed, use the data log to redo the transaction. So we have our transaction log, go redo the transaction as of the 23rd and update it and redo the transaction. If the transaction was rolled back, don't do anything because the data didn't change. Nothing was saved, so it's okay, we can ignore that. So that is the deferred write technique, which means we're just writing the committed transactions. The write through technique identifies the last checkpoint, same as the other one. If the transaction was before the checkpoint, don't do anything because we don't care. If the transaction was committed after the checkpoint, then we're going to update using those after values. So remember how I said the database log was going to store your before value and your after value. We are going to look at the transaction logs and we are going to update with the after values. If the transaction was rolled back, we are going to update using the before values because that was before the transaction, before it was rolled back. So both of these different techniques work. You can recover your database using either of them. They just do it a little bit differently. So depending on how your data is and definitely how your transactions are written might determine that you might want to do one versus the other. Okay, so that was chapter 10 on transactions. Transactions are really, really important in SQL to maintain that consistency, to maintain that integrity. So just to remember, a transaction is that logical unit of work. It's a way of describing an entire collection of statements or commands that can be combined together at one. If any one of them fails, they all should fail. We have our transaction properties, our atomicity, our consistency, our isolation, and our durability. So is it all or nothing? Is the data consistent with our constraints? Is the data isolated for data locks? And can the data be held accountable if there is a power failure or some other thing? How durable is it? SQL allows you to do commits and rollbacks and also do tries and catches. With our concurrency controls, the things that could happen, you could have your lost data, your uncommitted data, and your inconsistent retrieval. We can have locks at the database, table, page, row, or field level. Our lock types can be either that binary, either it's locked or it's not locked, and our shared exclusive where we have the option of being read-only or exclusive write ability to a single transaction. If we have serializable scheduling, can two transactions occur at the same time, or is there going to be a problem with data consistency? We can use timestamping to determine concurrency. And then, of course, the optimistic are locks really necessary. If you have lots of reads but not a lot of changes, you can do optimistic. And then we talked a little bit about how to use transactions to do data recovery procedures. Okay, so hopefully that was a lot on transactions, but hopefully it made some sense to you and you understood it. Let's talk about your homework. So for our homework, because this one's a little more cerebral, I do want you to do all of the review questions. I kind of went through and there were like 3 or 4 that I thought might be superfluous, but I actually kind of liked them all because I want to know if you understand. Please, again, use your own words. Please do not use my words. Do not use the book's words. Try to find ways of answering these questions using your own words, your own understanding of what's going on, because it's really hard for me to understand if you're just going to repeat word for word from the book. Did you actually get it or did you just copy? And then for the problems. So we're going to do problem number 1, which is an A through E. And then we're going to do problem number 6. 6 is going to have both an A and a B. It's going to be related to ABC markets. ABC markets, SQL create statements are in D2L. So you can go into D2L and get those create statements if you want to add ABC markets to your database. Don't add them to mine, add them to yours. And then 7 is related to both 6A and B. 8 and 9 are related to 6A, and then 10 and 11 are the same questions but related to 6B. It's going to be making your own transaction log. So understanding what piece of information go into a log, what is it going to look like? Okay. Please try to have fun with this chapter. I think transactions are great. So if you have any questions, please let me know and have a fabulous week.